We'll continue with the conformational analysis of disubstituted cyclohexane, and in this video we shall discuss about 1,2-disubstituted cyclohexane. In the last video we have seen about 1,1-disubstituted cyclohexane. Now 1,2-disubstituted cyclohexane, when we discuss, we need to consider a few aspects regarding the structure of the chair conformer. Now, when the substituents are above the plane, the substituents are present above the plane, are oriented above the plane, then we call it as beta orientation also. So here you will have one axial substituent in beta orientation and one equatorial substituent in beta orientation. And similarly, if they are oriented downwards below the plane, then we call it as alpha orientation, and we have here alpha, an equatorial alpha and an axial alpha. Now when the substituents on, suppose these are 1 and 2 carbon, when the substituents are on 1 and 2, and when the substituents are oriented beta beta or alpha alpha, we call it as cis conformer, okay, or it is it's a cis form. And if it is beta alpha or alpha beta, then we call it as trans form. Okay, so this concept you must keep in your mind regarding the alpha beta. Now if both the substituents are in the equatorial position, then we call it as EE. If both the substituents are in the axial position, we call it as AA. And if one of them is in equatorial and the other is in axial, we call it as EA or AE. Alright, so these terminologies, please keep it in your mind. Particularly this one, how do we name them, cis and trans? So the nomenclature comes from the facial relationship. Okay, so if the two substituents are placed beta to the plane, then we call it a cis, or alpha to the plane. Or you can say if both the substituents are placed on the same side of the plane, then we call it a cis, and if it is on opposite side of the plane, then we call it as trans. Now let's take up the conformers of 1,2 or conformations 1,2-disubstituted cyclohexane, particularly 1,2-dimethyl cyclohexane. Now we can write in the planar form 1,2-dimethyl cyclohexane, and if it is in the cis form, we can put it as like this in the plane. Now we know that it will not exist in the planar form, it will take up the chair conformation. And since it is a cis, since both of them must be on the same side of the plane, so here you have beta beta, that is both are above the plane, both the methyl groups are above the plane. So this is beta beta, and here we have alpha alpha, wherein both the conformer substituents are below the plane. Now if we flip beta beta, what happens? You get another conformer wherein the axial has become equatorial and the equatorial has become axial, but still it is beta beta. And here in the alpha alpha, the equatorial has become axial and the axial has become equatorial, but it is still alpha alpha. Both the groups are below the plane. So even on ring flipping, alpha remains alpha, beta remains beta. Alright, now we'll see which is more energetic. Is it the beta beta or alpha alpha? Both look same. Both are almost the same because there is one axial orientation or one axial substituent and one equatorial substituent in all these four cases. So all of them are going to contribute in the same manner. So let us now look at the energy level or energy of these conformers. So for that we can consider the diaxial interaction, or we can divide this molecule into butane units and then calculate its energy. Now when we look at the diaxial interaction, in the first conformer there will be two diaxial interaction with the axial methyl and the two hydrogens on carbon 3 and carbon 5. So 2,1,3 diaxial interaction over here. Same way when we flip, again we'll be having 2,1,3 diaxial interaction. And in the alpha-alpha case also, this axial methyl group will be having interaction with the axial hydrogen of this, the hydrogens of carbon over here and over here. So that also again contributes 2,1,3 diaxial interaction. Similarly here also. So when we look at the 1,3 diaxial interaction, all these 4 conformers are having 2 1,3 diaxial interactions. Now let us look into the butane units. Now we have the, I've taken here the axial equatorial beta version, the beta-beta molecule. Same will be for the alpha-alpha also. Now we shall number the carbon atoms 1, 2, 3, 4, 5, 6, 7 and 8. 7 and 8 for the substituents. This will be easy for us to identify the butane units, this numbering. Now let us consider the substituent 7, that is CH3 would be number 7. Which are the butane units which it will subtend? Now it will have 7, 1, 6, 5, and it appears to be a gauge butane unit. You can see the angle subtended by 7, 1 and 6, 5 is 60 degree. Then we can have 7, 1, 2, 3. 7, 1, 2, 3. That again is gauge. Now we can have another one, that is including the 8th substituent or the 8th carbon. When we include that, you get 7, 1, 2, 8. That is also gauge. Now these are the units, the butane units which has been subtended by the carbon 7. Now when we consider carbon 8, we have 8, 2, 3, 4. Now 8 is in the equatorial position, remember. So this will be, we have already seen when there is anti-conformer, when there is the substituent is in equatorial position, it gives anti-butane unit. In case of 1, 1, we have seen that. So here you have 8, 2, 3, 4, that is an anti-butane unit, and then we can even have 8, 2, 1, 6, that will also be anti, and we can have 8, 2, 1, 7, which is similar to the one which we had considered for 7. That's a common conform or common butane unit. So this will be gauge. So altogether in this conformer we have, how many gauge we have got? 1, 2, 3 gauge units and 2 anti-units. So altogether, along with the 6 gauge units of the cyclohexane, we'll have 3 gauge butane units and 2 anti-butane units from the substituents. So this conformer will be having energy almost 3 gauge units more than the cyclohexane, unsubstituted cyclohexane. So it will be almost 2.7 kilocalories per mole more energetic than unsubstituted cyclohexane. Alright, so in all the cases, let it be alpha-alpha or beta-beta, or its flipped form, in all the cases, this will be the same energy values. So the 1,2 disubstituted alpha or cis conformer will be 2.7 kilocalories per mole and having more energy than the unsubstituted cyclohexane. Now let us look at the chirality of this conformer. Now when you take the mirror image of this, the conformer or the form which we get is something like this. Now these two are now mirror images. Now when you take the mirror images, now this is beta-beta, the mirror image is also beta-beta, and this is axial equatorial, the mirror image is also axial equatorial, right? Now one more thing what we can see here is, in order to check whether it is superimposable, whether the two mirror images are superimposable, there is a small shortcut, we can rotate the molecule and check it out. Or what can we do is, you start from the substituent and take one full rotation or one full round around across this molecule. That is, take one full cycle. That is, if this is carbon 7 or this is carbon 7, you are taking 7, 1, 2, 3, 4, 5, 6. And you reach here. Alright, 1. So, and look, just make sure that you reach the next substituent at the earliest. Now you can make the full circle in this direction also, like 7, 1, 6. But it's better you take the direction like this, 7, 1, 2, so that the substituent is arrived at the earliest. Now when you move from this axial substituent to the equatorial substituent, you are taking this route, that is 7, 1, 2, 3, 4, 5, 6. So you're going clockwise. Now when you take the mirror image, it is again axial equatorial, it is again beta beta. But when you move from the axial substituent to the equatorial substituent, you are going in the anti-clockwise direction. See here, you're going 7, 1, 2 in the anti-clockwise direction. So since you are moving, this is like this, we can say that they are non-superimposable mirror images. That's one of the shortcut of identifying whether the cyclohexane conformers are superimposable or, mirror images are superimposable or not. Okay, the other way around is by rotating the molecule. Now, since rotation of the molecule is beyond the scope of this video, I'm taking up this route. So these two are non-superimposable mirror images, and hence they must be chiral. But unfortunately, these two structures or these two forms were not able to be separated. Scientists could not separate it. Now the reason for that is, we'll see, when we flip this, when we flip the molecule, we get this chair conformer wherein the axial substituent has taken up the equatorial orientation and the equatorial substituent has taken up the axial orientation. Now when we see, again, it is again axial equatorial, it is again beta beta. Now when you move from the axial to the equatorial, you take a round, you go from axial 1, 2, 3, 4. Now that you are moving in the anti-clockwise direction, right? You have to always, if you're fixed axial, so you have to start always from the axial. So you're starting from the axial on carbon 2. So when you reach the equatorial, you are taking the anti-clockwise direction. So this is almost same as the mirror image of this compound, right? The flipped conformer is the same as the mirror image of the compound, chair conform. And hence, these two are equivalent. You can say that the flipped form and the mirror image are equivalent. Now, since flipping happens every second or all the time, 50% of the molecule will be in this form and 50% of the molecule will be in the flipped form. And hence, we cannot separate the mirror images. Alright, so we call them as non-resolvable DL pair. Okay, and hence they will not show any optical activity, because they will be non-resolvable and they will be the mirror image and this will be flipping. So you cannot identify them and they will not show any optical activity. So they don't show optical activity. they are non-resolvable DL pair. They can also be called as conformational enantiomers. We had mentioned this earlier also about the conformation, naming it as conformational enantiomers, the flipped forms. Now, I said they don't show optical activity. In earlier, it was considered, when they detected that the 1,2 disubstituted or a dimethyl cyclohexane did not show optical activity, scientists thought that it was because they are meso. Now, when we look at a planar structure, we find that there is a plane of symmetry and they appear to be a meso compound. So the non-optical activity of the molecule was considered to be because of this. But it is not actually like this. When we write the chair conformer, we find there is no question of formation of a meso compound at all. So actually it is because of the presence of the because it is non-resolvable DL pair. Now let us consider the trans molecule. Now in trans 1,2 disubstituted dimethyl cyclohexane, we can write it in this way. Now in trans, one will be in alpha and the other will be in the beta form, beta orientation. So here you have this methyl group in the beta orientation and the other methyl group in the alpha orientation. So this is one way of writing. Another way is when we flip it, you get both these go to the equatorial orientation, right? Now this is this methyl group is in the beta orientation, this methyl group is in the alpha orientation. So the first one is AA, axial, the second one is EE, equatorial. Now these are the two possibilities for transform. Now if we take the mirror image of this, if we take the mirror image of the EE form, you get it like this. Now we know that energetically the EE form will be more stable because both of them are in the equatorial form, equatorial orientation, both the substituents. And in AA, since both the substituents are in the axial orientation, there will be 1,3 diaxial interaction above the plane and 1,3 diaxial interaction below the plane. So altogether there will be 4 1,3 diaxial interaction, and that will be going to increase the what we call the energy of this molecule. So this molecule will, or the trans compound will always prefer to exist in the equatorial conformation, that is EE. It will exist as EE conformer. Energetically, EE conformer is more stable, having lower energy. If we divide it into butane units also, we can find it. We'll do it later. Now, so we are taking the mirror image of this EE form. When we take the mirror image of this EE form, we find that they are again non-superimposable mirror images. So you can take this and keep it here. You will not get it as non-superimposable. You can see here, when we take the EE, both are EE, both are alpha beta, right? One is above the plane and the other one is below the plane. Here also this is above the plane, this is below the plane. But when we take a round around the molecule, when we start from this equatorial above the plane, beta equatorial, we go from 1, 2, 3 like this in the clockwise direction. Now when we start with the beta equatorial, we go in the anti-clockwise direction. Alright, so they are non-superimposable mirror images. But they are resolvable DL pairs. They are resolvable. Okay, now how was it resolvable? Well, because their energy, these two, the AAEE energies will be different, so they will not be flipping. Alright, and they can be resolved. So because their structures are also different. See, they are totally non-superimposable, and they will not be flipping to AA form. They will be remaining like this only. In the other case, in the cis form, the ring flipping was possible. Here, ring flipping will be restricted because EE is most stable. So, energetically, when we see this AA form will be having 6 gauge units of the cyclohexane and 5 butane units of the introduced by the 2 substituents. Among those 5, 4 will be gauge and 1 will be anti. In the EE form again, there will be 6 butane units from the cyclohexane ring and 5 from the 2 substituents. And out of the 5, 4 will be anti and 1 will be gauge. So when you see the energy difference between AA and EE, we find that EE is having altogether 7 gauge units, but AA is having altogether 6 plus 4, 10 gauge units. So 3 gauge units are extra in AA. So AA will be 2.7 kilocalories more energetic than EE, and hence EE will be the most stable conformer. Now we'll see, we'll dissect this into butane units and just check it out. Now let us take the AA form. Now in AA form, if we number the carbon atoms, 1, 2, 3, 4, 5, 6, 7 and 8. 7 and 8 for the substituents. Now you take the butane units with respect to the carbon 7 substituent having carbon, named as carbon 7. Now you see here you have 7, 1, 6, 5. That is a gauge unit. Another possibility is 7, 1, 2, 3. 7, 1, 2, 3, which is again another gauge unit. Now, another possibility is by including the 8th carbon, you get 7, 1, 2, 8, which is anti. You can clearly see the anti form. Now, in the same form, if we consider the butane units with respect to 8, subtended by carbon 8, then you have 8, 2, 3, 4, which again is gauge. Then we have 8, 2, 1, 6, which again is gauge, and also we'll be having 8, 2, 1, 7 anti, which is same as that of the earlier case. So altogether we will be having 5 extra butane units, of which 4 are gauge and 1 is anti. Now take the case of the equatorial EE form. You number them 1, 2, you are flipping this. In fact, you are flipping this AA into EE. So 1, 2 will be here. 3, 4, 5, 6, 7 and 8. Now, if you consider the butane units with respect to carbon 7, you have 7, 1, 2, 3. 7, 1, 2, 3. That is anti. And you can also have 7, 1, 6, 5, which is again anti. Okay, and you can have, when you consider the other substituent, you can have 7, 1, 2, 8 or 8, 2, 1, 7, both the same. That is gauge here. Now, so here with respect to carbon 7, you have got 3 butane units, out of which 2 are anti and 1 is gauge. Now with respect to carbon 8, you have 8, 2, 1, 6, which is anti. Then you can have 8, 2, 3, 4, which is anti. And also again 8, 2, 1, 7, which is gauge here. Okay, so altogether 5 extra butane units are introduced, out of which 4 are anti and 1 is gauge. And we know that the energy with respect corresponding to anti, we are considering at 0. So this molecule will be having 1 gauge butane unit extra. So altogether here there will be only 7 gauge butane units, but here we will be having altogether 10 gauge butane units. So the difference is 3 gauge butane units, that is again 2.7 kilocalories per mole. So AA will be having 2.7 kilocalories per mole extra energy than EE. And that's why EE is considered to be more stable. So in case of trans isomer, EE conformer is more stable. Among cis and trans of 1,2 disubstituted cycloalkanes, the trans isomer will be more stable because it has got the EE form, while in cis we have AE form, which is having almost 2.7 kilocalories per mole extra energy than unsubstituted cyclohexane, and also 2 Gauch butane units more than the EE form. Okay, so here we have when you consider the 1,2 disubstituted cyclohexanes, the trans form is most stable with EE conformation. Okay, EE orientation of the molecule substituents. Hope it's clear to you. Please do draw the structures and practice yourself and make yourself thorough. Thank you so much.